Good morning. This is Math 111. Today we're going to continue on with section 8.2. In 8.2, in our last lecture, we talked about the quadratic formula. We're going to talk about the quadratic formula some more, but this time in the context of word problems. Using the quadratic formula frees us up in a sense in that we can, we're not restricted to equations that can factor. And we can perhaps investigate perhaps more interesting applications than we could without the quadratic formula. Let me give you an example of what I mean. I want to look at example 5. This is on page 767 in your textbook, and you might want to turn there. It's a worked out example in your book. Turn there and read along. I'm going to read the problem here over the phone. Shortcuts. Instead of using the hallways, students are wearing a path through a planted quad area to walk 195 feet directly from classrooms to the cafeteria. If the length of the hallway from the office to the cafeteria is 105 feet longer than the hallway from the office to the classrooms, how much walking are the students saving by taking the shortcut? Alright, refer to the picture on page 767 in example 5 in your textbook, and I'll copy it here. Basically, we've got a situation where we've got hallways, we've got classroom or a set of classrooms here, we've got the school office here, and we've got a cafeteria here. Alright, the implication here, these hallways exist at right angles to each other, and students are walking from classroom to the cafeteria. Alright, they want to know how much walking are they saving by taking the shortcut, and they tell us explicitly that the shortcut is 195 feet long. Alright, well, our goal then is to find out the path from the class to the cafeteria through the hallways. Of course, they don't tell us that explicitly, but they do tell us the length of the hallway from the office to the cafeteria is 105 feet longer. Alright, so I'm going to let x be this distance from classroom to office, and then x plus 105 is going to be the distance from office to cafeteria. Alright, so I want to solve for x, and then find out the total amount of walking that's being saved. Alright, clearly in a right triangle, well, we know that the hypotenuse squared is the sum of the squares of the two legs, right? A squared plus b squared equals c squared by Pythagoras theorem, right? Alright, we're all familiar with that, so what I can do is then square the legs of these triangles, of this triangle, this right triangle, add up those squares, and then set that equal to the hypotenuse squared. Alright, so with those substitutions I get this equation, and clearly I'm going to get an equation of degree 2 that I can solve, hopefully by the quadratic formula. Alright, so I'm going to solve for x here. Let me move over here. If I square x plus 105, I'll get x squared plus, well, the inner and outer products will be 210x added together, and the last product is going to be 105 squared. Is going to be 11025, and 195 squared on the right hand side is 38025. Alright, what I'll do now is get everything in standard form, combine like terms, and get terms in decreasing degree over on the left hand side. Well, x squared plus x squared on the left is 2x squared plus 210x, no other x term. I'll just subtract 38025 from both sides, and I end up with minus 27,000 equals 0. Alright, so perfect setup for the quadratic formula now, but I notice first here everything's divisible by 2, including 0, so let me clean things up a little bit. Divide everything, all terms, by 2. Get the magnitude of these numbers down as much as I can before I plug in to the quadratic formula. Alright, so I'm going to, let's see, I might have a shot at factoring this, but I'm not at all comfortable with that, with this large number here. It has a large number of possibilities, and I'm not sure I would be able to spot the proper factors, even if it was factorable. So I'm going to use the quadratic formula with A is 1, B is 105, and C is a negative 13,500, and substitute then into these values into the quadratic formula. So x equals minus b plus or minus the square root of b squared minus 4 times a times c that old mess over 2 times a. Alright, so with little patience and good housekeeping, I'm going to continue on here. X then equals minus 105. I'm going to crunch together this stuff under the root sign, the radicand, plus or minus the square root of, if I work it out with my calculator, I get 65025, then divided by 2 times 1 is 2. Alright, I'm thinking the square root of 65025 is a whole number, I hope. And it is, right? The square root of 65025 is 255, so I get that from my calculator. Oops. Classic mistake there. The square root of 65025 is 255, no root sign there, right? Divided by 2. So x equals, well, 255 minus 105 is 150 over 2, or x is minus 360. If I take minus 105 and subtract 255, I get minus 360 over 2. Alright, so for final solutions for x, I get 150 over 2 is 75, or minus 360 over 2 is minus 180. I'm going to eliminate this negative length. Let me make a comment here. Sometimes negative solutions are okay, but not when you're talking about lengths. Alright, so no negative length, so I call that an extraneous solution. So x equals 75 feet. Alright, now they ask us how much room or how much walking is saved. Well, let's see. If x is 75, then the x plus 105, the distance from the office to the cafeteria, is going to be 180. Right? So if I walk 180 plus 75 feet, that's going to be 255 feet from the using the hallway. All right, so let me write that down. Using the hallway, I walk a distance of 255 feet. Using the shortcut, again, the book tells us that's 195 feet. So the difference between 255 and 195, of course, that's 60 feet. So that's 60 feet of walking saved. That's what they wanted. They didn't want the length of the distance from office to classroom and office to cafeteria. The book explicitly asked for how much walking is saved. Alright, so in that light, the answer, or the final answer, would be 60 feet. Okay? Alright, I want to take a look at another one, another application of quadratic type formula. This one's number 77. I believe this one's in your homework list on page 772. Alright, number 77 on page 772. Let me turn there. Alright. talks about IMAX screens. You might want to read along with me in your book. The largest permanent movie screen is in the Panasonic IMAX Theatre at Darling Harbour, Sydney, Australia. The rectangular screen has an area of 11,349 square feet. Find the dimensions of the screen if it is 20 feet longer than it is wide. Alright, so we are claiming this is a rectangular screen. So I'm going to draw a picture here. A rectangular screen. It's supposed to be straight lines. We know the area of this rectangular screen in square feet is 11,349. Okay. Alright. We are also told that the screen is 20 feet longer than it is wide. Alright, I'm going to call this the width, and I'm going to call this the length, and we are told the length is 20 feet longer than the width. Alright, so I think you see where we're headed here. We can easily get an equation of degree 2 to hopefully solve with the quadratic formula, because I know in a rectangle, width times length equals area. So let me write that down. Width times length equals area in any rectangle. Alright, so there's a setup, and I'll clearly get an equation of degree 2 out of this. I want to solve for the dimensions of the rectangle. Alright, so if I multiply things out and subtract 11349 to get things in standard form, here's what my degree 2 equation would look like. And again, I may be able to factor this, but 11349 makes me nervous. I'm not sure I could spot the proper factors even if I tried to factor this. So I'm going to go right to the quadratic formula. The quadratic formula always works. And with the numbers being so cumbersome, of course, I'm going to employ the use of a calculator. Alright, so I'll make my substitutions. W equals minus b plus or minus the square root of b squared minus 4 times a times c all divided by 2a. Okay. Alright, of course I'm going to simplify this radicand expression first and then see if I can find the square root. So w equals minus 20 plus or minus. Alright, if I punch this out on my calculator, I get under the root sign 45796. And then divide by 2. Alright, I'll punch in the square root of 45796 on my calculator, and I get 214. Alright, that is fortunate. Alright, so I'm going to have two solutions for w. One of them is going to be negative, so w equals, well, if I embrace this positive option here, I'll get 194 over 2. Which gives me a solution of 97 feet for w, or, well, minus 20 minus 214 is going to be negative 234 over 2, and I'm going to throw that out as a extraneous solution because it's a negative length. You write that down, no negative length. Alright, so if w then is my only solution for the width, then my length, of course, is w plus 20, and that's going to be 117 in feet. So the dimensions of my gigantic movie screen is going to be 97 feet by 117 feet. Okay. Alright, let me get to another screen. I'm on site number 79 in our book. I believe this is in the homework assignment. Number 79. This is on page 772. Talks about parks. Alright, you might want to read the problem along with me. Central Park is one of New York's best known landmarks. Rectangular in shape, its length is 5 times its width. Alright, let me draw a little picture here. So I'm going to draw a crude diagram of Central Park. It's rectangular shaped, and its length is 5 times its width. So I'm going to call the width W, and then the length I'll call 5W. Right? When measured in miles, its perimeter numerically exceeds its area by 4.75. Find the dimensions of Central Park if we know that its width is less than 1 mile. Alright, well, we talk about the book's describing a perimeter and area. Well, I can't tell you what the perimeter is in feet, but I can tell you what it is in terms of W. If you got a rectangle with opposite sides of equal length, if I add up all these sides of the rectangular area, I get 12W. 5W plus 5W plus 2W plus 1W plus 1W is 12W. Okay? Similarly, I can't tell you what the area is, but I can tell you in terms of W what it is. The area is going to be your length times your width. W times 5W is 5W squared. Now we are told in the book that the perimeter exceeds the area by 4.75. Alright, so I can get an equation out of this. I'll say my perimeter is 12W, and that exceeds the area by 4.75, so it's going to be your area plus a little bit. Perimeter exceeds the area by 4.75. Alright, so I can get a degree 2 equation to solve out of this fairly easily. Alright, I'm going to then subtract 12W from both sides. And I'm going to now invoke the quadratic formula. Of course, I'm going to be using a decimal value for C. We haven't done that yet, so not a big deal, I hope. Alright, so it's in standard form, so I'll label my A, B, and C values as shown. So now W equals minus B plus or minus the square root of B squared minus 4 times A times C, and I'll plug in 4.75 for C, all divided by 2A. Okay, so there's my substitution into the quadratic formula. I'll grind out this expression under the root sign, the radicand. First, minus 12 is positive 12, plus or minus. Alright, I get a 49. 12 squared is 144. 4 times 5 times 4.75. If you crunch that together under the root sign, I get a 49, and that looks convenient because we all know what the square root of 49 is. Okay. So W then equals 12 plus or minus, well, the square root of 49 is 7 over 10. So with the plus option, I get 19 over 10, which is 1.9 in miles, or 12 minus 7 is 5, and 5 over 10 is 0.5 in miles. So I've got two solutions for W. One of them I'm going to throw out. Notice they're both positive. I'm going to throw this one out because if you look in the problem statement, it says find the dimensions of Central Park if we know that its width is less than 1 mile. So this is not less than 1 mile, which was a condition stated in our problem, so I scratch it. So my width is going to be 1/2 mile, and the length is 5 times the width, which is, of course is going to be 2.5 in miles. Right? So the width is 1/2 mile, the length is 2.5 miles. Alright, so that was 79 in our book. I also want to talk about number 82. And number 82 is a little tougher, kind of a geometry application. A pretty standard problem, really. Let's look. Number 82, this is on page 772. Alright, let me read the problem. Metal fabrication. A box with no top is to be made by cutting a 2-inch square from each corner of a square sheet of metal. After bending up the sides, the volume of the box is to be 220 cubic inches. Find the length of a side of the square sheet of metal that should be used in the construction of the box. Round to the nearest 1/100th. Alright, so what we're starting out with is a square piece or sheet of metal. It's supposed to be square. And I'll say it's X units long. Okay, each side is X inches wide. Okay. Alright, now what we're going to do is take 2-inch squares from each corner. Alright. And then what we're going to do is on the purple lines I'm going to bend up these flaps, these tabs on the side, to make an open rectangular box. Okay. Alright, now hopefully we can see that this when I bend up these tabs to form the box, well, clearly these tabs are 2 inches wide off the corner, so that makes the height of this box 2 inches. Similarly, the purple lines here represent the base of that open box. Each of these bases is X minus 4 units wide. Why X minus 4? Because I started out, this side was X units wide, and if I take out 2 inches from each side, that's X minus 4 is the length of this tab here. Alright, so I can now set up a formula. We know that the volume of a box is always length times width times height, right? Well, the length and the width is X minus 4, and the height, as we know, is going to be 2. So that's an expression for the volume of my box. X minus 4 times X minus 4 times 2. And the book tells us that the volume of this box is 220 cubic inches. Alright, I think you can see now we'll have an equation of degree 2 that I can get in standard form and hopefully use my quadratic formula. First thing I'm going to do is divide both sides by 2. That'll cancel that 2 out, and I'll get 2 goes into 220 110 times on the right hand side, so that'll simplify things a bit right off the bat. So I end up with the equivalent equation now. X minus 4 times X minus 4 equals 110. Alright, I'll multiply the polynomials on the left-hand side, so I get x squared is my first product, minus 4x gives me a minus 8x for the inner and outer product, plus 16 for the last product equals 110. And now I'll subtract 110 from both sides to get minus 94, and then of course equals 0 on the right. Alright, I'm going to use my quadratic formula here again with a equals 1, b equals minus 8, c equals negative 94. So x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Alright. So x equals, now simplifying, 8 plus or minus the square root of, again, if I crunch these numbers together under the root sign, of course, I get minus 8 squared is 64. Minus 4 times 94, I get a radicand of 440 under the root sign, and that's not a perfect square. So I'm going to have to do some estimating here. Alright, if I punch 440 and take the square root with my calculator, I'll say x is approximately equal to 8 plus or minus, well, the book says to round this off to the nearest hundredth, so I'll round that square root off to the nearest 100th. So 8 plus or minus 20.98 over 2. And the worst is over. I'll have a plus and a minus option here, of course. If I add 8 to 20.98, of course, I get 28.98 over 2, which is, of course, 14.49 in inches. Or, well, 8 minus 20.98 will give me a negative number, and I'm not even going to bother to figure it out because we cannot have a negative length. Remember, x was our length of our original piece of steel in this problem. Alright, so my final answer is 14.49 inches, and that's rounded off to the nearest hundred. Alright, this brings us to the 28th minute, so we'll call it a day. And this concludes section 8.2, quadratic formula, word problems.